Electrons can be divided into whether they are core or valence. The core electrons are the ones on the inside, like the core of a planet or apple. They have lower levels of N. The valence electrons are the electrons in the outermost shell. They have the highest level of N for that particular atom. For example, in sodium, the 1s2, 2s2, 2p6 are the core electrons because they are in the first and second energy levels. The 3s1 electron is valence because it is in sodium's outermost energy level, N equals 3. The core electrons will always have the same electron configuration as the previous noble gas on the periodic table. The previous noble gas to sodium is neon, which has the electron configuration 1s2, 2s2, 2p6. Instead of writing all that out for the electron configuration of sodium, we can write neon in brackets to replace sodium's core electrons, since it's the same exact electron configuration. These condensed or noble gas configurations save us time and allow us to focus on the valence electrons, which are the important ones that actually do the reacting. This figure shows the valence electron configurations for all the elements in the periodic table. Basically, it is the condensed configuration without writing the symbol for the core. What we can notice is that there are patterns in the electron configurations as you go down a group. We can summarize the patterns for each group with a generalized electron configuration. For example, we can write 1a as core NS1. For example, lithium has a helium noble gas core and then 2s1 for its valence electron. Sodium has a neon noble gas core and then 3s1 for its valence electron. In the same way, we could write the generalized form for 2a as core NS2. For example, beryllium has a helium noble gas core and then 2s2 for its valence electrons. Magnesium has a neon noble gas core and 3s2 for its valence electrons. See if you can come up with generalizations for the other groups in the periodic table. The great thing about using the group numbering system with the A's and B's is that for the A's, the group number equals the number of valence electrons. For example, boron's valence electrons are 2s2, 2p1. 2 plus 1 is 3, so boron has 3 valence electrons, and it is in group 3a. Although our method of finding the electron configuration of elements works for almost all of the elements on the periodic table, it does not work for all of them. One exception to the filling order is chromium. We would expect, based on what we've learned so far, that its electron configuration would be argon core 4s2 3d4, since it is the fourth element in the 3ds. Experimental evidence shows, however, that its electron configuration actually is argon core 4s1 3d5. You can think of it as an electron moving out of the 4s and into the 3d. We rationalized this discrepancy by saying that having a half-filled 3d subshell makes the atom more stable and therefore having a lower energy. Similarly, we would expect the electron configuration of copper to be argon core 4s2 3d9, but it's actually argon core 4s1 3d10. We use a similar rationalization. Having a completely filled 3d subshell is more stable and therefore more energetically favorable.